enthalpy and what that is. And then homework, just, I don't know what day you're watching this on, just make sure that you're following the calendar on the website, because all the dates and everything that you need to know is on there. So this is the first lesson of Unit 9. So we're following the Unit 9 calendar, and everything that we're doing is on the Unit 9 page. So on the top of the worksheet that you should be following along with is your yo-yo. So if I am not your chem teacher, that is what I call a do now. So essentially, we've all done CERs. So here's a pretty quick one. This one says, when we gave you the claim, breaking bonds are considered to be endothermic processes, and forming bonds are considered to be exothermic processes. So, and we gave you that emoji as kind of a hint. So what you should be thinking of is barf. So when you break a bond, energy has to be absorbed. So if you think about breaking a pencil, it doesn't just randomly break. You have to put energy into it for it to break. And then if you release energy, that means a bond is formed. So right now, if you want to just clap your hands together, when you put your hands together, you're essentially forming a bond, and you hear a sound. You hear that clap. That's that energy being released. So if you're reasoning, if we know endothermic is absorbing energy, that must mean breaking a bond is an endothermic process. On the opposite hand, we know exothermic means releasing energy, and according to Barf, releasing energy bonds are forming. So essentially we can say breaking bonds is endothermic and forming bonds is exothermic. So first thing we want to talk about is heat of reaction. So we talked about, again, something endothermic, energy being absorbed, something being exothermic, energy being released. Now you can actually quantify that number about how much is released or gained, and that's what the heat of reaction is. So if you were to look this up in a textbook, you'd get the definition for it to be the amount of heat energy lost or gained throughout the reaction. So with heat energy, that is also the same as thermal energy. Those things will be kind of used accordingly. So one thing that's new here is the heat of reaction. So you can essentially measure this by taking the heat of the products minus the heat of reactants. And so remember when we did the Q equals MC delta T equation, and we said delta T was the final minus the initial temperature? Well, heat of reaction is the same thing. So if we have, for example, A plus B produces C and D, change pen colors, A and B, these are your reactants. And in order for a reaction to happen, you need your reactants. And then you are producing your products. So essentially we can say that your products are your final and your reactants are your initial. So essentially it's the heat of the reactants, the heat of your products, your final, minus the heat of your reactants, your initial. And so that number, that delta H, that change in heat, is enthalpy. So the fancy word for it is enthalpy. Now I like to remember it as, or write it like this with a big H, because all this means is that we're talking about heat. If we're talking about enthalpy, we're talking about heat, because there is a word that we'll learn later on that looks similar but has a completely different meaning. So, going into endothermic reactions. Again, this is when heat is being absorbed, and it's being absorbed by the reactants. So again, you have your reaction down here. Your reactants are before the arrow. Your products are after the arrow. So all this energy that's then being absorbed by the reactants is stored in the bonds of the products. So if you were to calculate delta H and do, final minus initial, so products minus reactants, that delta H value is going to be positive. So and we'll work through an example on the next slide. So endothermic reactions, positive delta H. And if it's being absorbed by the reactants, it's written as a reactant as well. So it's written before the arrow. And again, we'll practice this a bunch of times moving forward. So example, let's use the reaction A plus B equals C. So if we have A plus B gives us C. So the question says we have A has a energy of 40 kilojoules and B has an energy of 20 kilojoules. So that means in total the reactants are 40 plus 20. So we have in total 60 kilojoules for these reactants. Then it's saying, okay, cool, HC is 110 kilojoules. Now, does 60 equal 110? No, that doesn't make any sense. Our reactants are a lot less than the products. And just going with conservation of energy, both sides have to be the same. So essentially what you need to think of is how much do we need to add to the reactant side to get the product side to be the same. So essentially you can set up an equation that essentially is 60 plus x gives you 110. So then subtract 60 from both sides, you get x equals 50 kilojoules. So essentially what that means is that A and B absorbed 50 kilojoules of energy to give you the product of C. Again, energy needs to be the same on both sides. So again, we're going to write this as a reactant because that means that 50 kilojoules of energy was absorbed. Now again, if it's absorbed, it doesn't just magically disappear. It's now stored in the products. Moving forward with exothermic reactions, this means that heat is going to be released as a product. So if you were to calculate delta H, again, that the heat of your final, so your products, minus the heat of the reactants, your initial, you're going to get a negative value. Now these are generally more stable and these are spontaneous. So what spontaneous means it's its own. So if you think of like a piece of bread going bad, or fruit or something just that happens by itself, it will happen regardless of what you do to it. So a spontaneous reaction will happen without any input of energy at all. So an exothermic reaction, again, we're talking about heat being released. So heat is going to be a product. So in this example, we have our reactants A and B, and then our products C and D. But because it's exothermic, we're also going to have that release of energy. So let's work through an example. Again, we're going to continue with the A plus B gives us C reaction. And here, it's telling you that A has a heat of 60 kilojoules. B has a heat of 40 kilojoules. And so in total, our reactants have 100 kilojoules of energy. So now it's saying that the heat of C, is 30 kilojoules. So again, 30 does not equal 100. So something is not right, and that means that we're missing energy on the product side. So what we're going to have to do is figure out how much energy is missing. So again, you set up your simple equation. 100 equals 30 plus x minus 30 from both sides. You get x equals your 70 kilojoules of energy. So here you're writing it as a product. So one thing I want to point out here is that your delta H value, again, if we're exothermic, we had said our delta H value is going to be negative. So here technically you see a positive number, but your delta H would be negative 70. So what this negative means is that negative essentially just means released. So you're releasing 70 kilojoules. But when you write it in the reaction, you'd never, ever, ever, ever write minus 70. In your reaction, you never, ever, ever have minus signs. Again, we'll practice questions with this later on, so if you're kind of confused right now, don't worry. So all of these reactions Well, all the reactions you're responsible for are on your reference table under table I. So table I has the heat of reactions at, 101.3 kPa and 298 Kelvin. So it's saying the delta H values are based on the molar quantities of these reactions. And a minus sign represents exothermic. So that this highlighted statement is literally on the bottom of your reference table. It's telling you that if you see a negative delta H value, that you have an exothermic reaction, meaning your energy is going to be released, which means you have to write it as a product. So if we have a delta H that is positive, so you can write these things in two ways. If you have a delta H that is positive, you can write your equation as is. So we're looking at this example here. And there's on the side, we're like, okay, cool, delta H is positive 182.6. That's a completely accurate way of writing it. But again, you can put that into your equation and make your equation look fancy and complicated. So again, this delta H being positive means it's endothermic, which means energy is being absorbed, which means it is going to be written as a reactant. So here, now you're just attaching that 182.6 as one of your reactants. So one of those things before the arrow. Oppositely speaking, if your delta H is negative, you can kind of put it off to the side and say, okay, delta H is negative. There it is. Or you can write it in your equation. Again, a delta H that is negative means it's exothermic. So heat is being released. And so there it's going to be written as a product. So again, all that negative sign means is literally the word release. So it released that much energy. But when you write it in a reaction, if it's being released, you're writing it as a product. So the placement in the reaction is essentially the sign of delta H. If you have a negative delta H, it's written as a product. Yes, there is a positive sign here, but because it's after the arrow, because it's a product, that means it is released. So it means it's a negative delta H value. Again, like I was trying to say before, you will never, ever, ever see something like this. So you have your reaction plus this minus 890.4. You will never, ever, ever see a negative sign in a reaction. So this is absolutely no, do not do that ever. Okay, so the way they make these table I questions is it's literally right in front of you, but the reader just likes to complicate it a little bit. So essentially, they can take what's on table I, flip it, or kind of change the ratios of it. So if a question asks you about a reaction and it is opposite of what it says on table I, all you have to do is switch the sign of delta H. So if table I says it has a reaction going this way, and it says delta H is negative 571, if you flip it, that means you're doing the reaction in the reverse direction. Sometimes reactions can be both forward and reversible. So if you reverse the reaction, all you have to do is reverse the sign of delta H. So the opposite of negative 571 is positive 571. So in this case, the reverse reaction would now be endothermic, because you have that positive delta H value, which means energy is being absorbed. So when you reverse reactions, you're just switching the signs of H. You're not doing anything to the actual number, we're just switching the signs. Okay, so here we have a practice question. Take a second, try to look at it. You need table I as well, but I also did give you this. So here it says how much, given this reaction, how much heat would be released if 4 moles of carbon dioxide were consumed. So this is what the reaction on table I says. It says you have 2 moles of carbon dioxide. Again, these coefficients represent the moles. So you have an invisible one there. So if it says moles, you don't have to calculate moles or anything. It's just looking at the coefficients. So if we have 2 carbon dioxides and that whole reaction shoots out negative 556 kilojoules, if you double the amount of carbon monoxide, that means you're doubling the amount of heat that's released. So in order to get from 2 carbon dioxides to 4 carbon dioxides, you're doubling the amount of stuff. So that means you have to take your delta H, which is 566, and double it. So if you were to double 566, you would get, let me take out my calculator, because I do not have it out, 556 times 2 equals, so your delta H is negative 1112 kilojoules. So now that we've doubled the reaction, we didn't do anything to the sign, we just doubled the amount. So if you're doubling the reaction, you're doubling the number. Okay, so here we give you a reaction, and it's saying, okay, calculate delta H for the following reaction. So if we go from the original given one to the one the question is asking, all you did now was cut everything in half. So now, if you have delta H as negative 571.6, and now it's asking for the reaction, the delta H for the second reaction, all you have to do is half that delta H value. So half of this would be 571.6 divided by 2 gives you, so your delta H for the new reaction is negative 285.8 kilojoules. So again, we didn't change the order of the reaction, we cut it in half. So if you cut the amount in half, you have to cut the heat in half. Okay, so there are some questions on the bottom of your page. Try them, and essentially what you need to remember, if you double the amount of the reaction, so you're doubling all the coefficients, you double delta H. If you half everything, you half delta H. Nothing happens to the sign. Then, other questions could be, if you switch a reaction. So if it says a negative reaction, if it says negative H on table I, and you go backwards, it's now positive. So when you switch the reaction, you switch the sign. When you double the reaction, you double the actual value. So try the practice questions. The key is posted. Good luck.